In this example, we are given a temperature distribution for a wall of thickness 0.2 meters. This wall is immersed in a fluid that has a bulk temperature, T infinity, of 100 degrees C. The given temperature distribution, or T of x, is equal to 200 degrees C plus negative 200 degrees C per meter x plus 30 degrees C per meter squared, x squared. We are asked to solve for three things. The first is the heat flux, or Q double prime, at both faces of the wall. The second thing we're asked for is the rate of heat storage in the wall. And finally, we are asked to find the heat transfer coefficient, or H, of the fluid on both sides of the wall. So let's start with the first problem. We know that Q double prime is equal to negative K times dt dx. And since we're given K, we can solve for dt dx by taking the derivative of our original temperature distribution with respect to x. So dt dx is equal to negative 200 plus 60x. So plugging in for x equals 0, because we're solving for q double prime at x equals 0, we find that q double prime is equal to 200 watts per meter squared. Now, the reason the degrees C and the Kelvin cancel out is that we're dealing with temperature differences. So now let's solve for the heat flux at x is equal to 0.2 meters. So to do that, we plug in the same values, but instead of plugging in x equals 0, we'll plug in x is equal to 0.2. This is equal to 188 watts per meter squared. So now we're going to move on to the second question. We know that heat generation, which we'll call E gen, is equal to the energy in minus the energy out. The energy in is just our answer for Q double prime at x equals 0, and the energy out is 188 watts per meter squared, or the heat flux out of the wall at x equals 0.2. And so this means that our energy generation in the wall is 12 watts per meter squared. Now we'll move on to question 3, which asks us, what is the heat transfer coefficient of the fluid at both x equals 0 and x equals 0.2? So we know that the heat flux in at x equals 0 has to be equal to H, our heat transfer coefficient, times the temperature at x equals 0 minus the temperature of the bulk fluid. We have our temperature distribution, which was given, and if you plug in x equals 0 to that temperature distribution, you find that the temperature at x equals 0 is equal to 200 degrees C. Now, solving for H, we find that H is equal to 2 watts per meter squared Kelvin. Now again, in this instance, a difference of 100 degrees C is equal to the same difference in Kelvin, which is why we can put the units in H in Kelvin instead of degrees C, because that's a more standard unit notation. Now, let's go into the heat flux at x is equal to 0.2 meters. We can again plug in x equals 0.2 into our original temperature distribution, and we find that the temperature at x equals 0.2 is equal to 161.2 degrees C. Solving for h, we find that h at x equals 0.2 is equal to 3.07 watts per meter squared Kelvin.